So what I'm trying to say is just a very simple. It's more questions than answers, and a very simple setting. But I still I want to tell you some arguments which I learned from Linda Westrick and Jan Reimann, and also from the most strange argument was communicated to me by Misha Raskin from Ilya Bogdanov. It's just a combinatorial question. He found an extremely strange and funny and nice argument which can be used for our purposes. So I'll try to do this. So I tried to prepare some writings on the board, but they are very just to remember what I planned to say, but not really. So for the newcomer, there is a reference to Blackboard in chat. That is so if you can have some device to write on it, it will be nice.
Just before we start, if some of the participants has troubles with sound or with the picture, please complain. Then we can try to
yeah.
So to kill the video.
Your sound is a bit too loud in terms of.
And your sound is a bit metallic.
Okay, that's difficult to do something about this.
Okay, is it better now?
Yeah.
1, 2, 1. Okay.
No, that's okay. But the cat is missing. I don't know. Also, maybe somebody wants to have a Russian subtitles, but we don't have ones. So.
So you're free to write Russian subtitles on the flight if you want to.
Yeah. Okay. So should we start, or I think we can. I will say some general things. So maybe if somebody comes later, it's Misha comes. So I think we can.
Yeah, I think now we can.
No hope probably that Sasha Rubtsov or Simonov will come. So maybe we start now. So I want to consider a general question, which is motivated by some question in. Not really motivated, but somehow inspired by the question about dimension and line of lines and points. But we don't need to know anything about dimension. I think I can say something later. But just we have a very simple picture. We have a graph, two bipartite graph, which finite graph, which is somehow, let's to make things simple, let's consider symmetric graphs. So we assume that every edge is as good as any other edge, which means that, for example, if we have two edges, for every two edges, there exists an isomorphism that maps E1 to E2. So all edges somehow are the same. And still, of course, they can have different complexity. And the vertices can have different complexities. So it's kind of, we want to understand how different can the complexities be if the graph is so symmetric. So, for example, for this we know that it has some fixed degree, because if any two edges can be mapped to each other, then of course every two vertices can be mapped. Okay, we assume that there are no edges, no vertices which have no edges. So it has constant degree.
Excuse me, it's probably not very important. Do you mean that your graph is edge transitive as a bipartite graph, or you assume that there is a symmetry which exchanges vertices from the left and
no, of course, I don't want to exchange the both sides. No, in our example, it could be symmetric, but I don't really realize this is not thing which we would like to do. So it's edge transitive as a bipartite graph. And then the question is very simple. So imagine we know complexity of some vertex x. And so what is the complexity of its neighbors? Or what is the complexity of edges? One can also ask
do we assume that the complexity of graph is some small?
Yeah, we assume that graph is something very simple, known, and fixed in advance. So of course we consider it actually a family of graphs, because otherwise it doesn't make any sense. And what I suggest is to consider two basic families. The first family is with edge x. So edge x, y are binary strings, and they are connected by an edge if they have a Hamming distance is small, some fixed constant. And of course they are symmetric in this way.
Excuse me, if the condition is that the distance is less than some threshold, then I'm afraid it's not edge transitive. Possibly you want to say that the distance is exactly something.
Probably we can. Yeah.
But in general, why do you need these conditions?
Why do I need it?
About symmetricity or something like that.
No, I don't need it actually. No, because I didn't. Still, I just want to. It's kind of motivation that actually our graph should be more or less the same everywhere, and we just still want to study complexity of different things. So let's forget about it. And another thing, it's just a line graph. We can have points and lines, and we have some incidence relation. So, for example, we have a finite field F. We have a two-dimensional plane, and on this plane we have some points, and also we have some lines. And this is what our main example today, at least for the simple proof which I want to explain. And what is actually convenient, I don't know if everybody is let me go to the next page. If everybody is happy with projective plane, it's more so we can consider a line which is ax plus b, but it's better more symmetric to consider lines like this, and even to consider add additional variable z. So as usual, we have x, y, z, and we have a plane z equals 1, and we can draw lines on this plane, but they are also planes in the three-dimensional space, and this makes things more symmetric. We need to add, so now we have also except for points like here, which are one-dimensional lines, we also have horizontal lines. So we add this infinite points, and there is even the infinite line, which is a horizontal plane, which contains all infinite points, and this makes things symmetric. So actually, we can consider xyz triples xy up to multiplication by a constant, and the relation is now symmetric. ABC is related to xyz if ax plus by plus cz is equal 0. And this is more or less the same as line this point, except for this special additional line and additional points. And but of course they are exceptional, so they have very small complexity, and so we really don't care about them. But it just makes things more symmetric. But if it's somebody doesn't like this, we can ignore this and consider lines and points. But okay, now the question. So imagine I can say theorem. Imagine a line has complexity. No, if our field contains 2 to the n elements, then a line, there are 3 coefficients a, b, and c up to a constant factor. So we have actually 2 to the 2n. If to be exact, it should be that many lines or points. And at any line, each line has 2 to the n plus 1 points, actually. But this is, so imagine, so the line has complexity normally between 0 and 2n. So if line has complexity x, then the maximal complexity of a point is n plus s, unless it is greater than 2n, in which case we use 2n instead. So actually, of course, line contains 2 to the n points. So we need at least n bits, at most 10 bits, to specify any point on the line. So so we cannot have more than n plus s. And the theorem says that we achieve n plus s unless if it's possible at all, which means that if it's not bigger than the whatever can happen for a point in general. So this is the theorem.
A question.
Yeah.
Are you saying that the maximal is n plus s or 2n?
Maximal complexity.
Or you're not saying that for most points in the line you have approximately this complexity?
Actually, it will be for most points on the line. But now what I'm claiming, what was stated in the theorem, it's just maximal complexity, but it will be for most points of the lines. Okay, so I think now it's let me see what I have on the next page. Okay, and the next page I have some picture. It doesn't contains anything, but still let's look at this picture again. So we have about 2 to the n. Here we have lines, we have points, and therefore the number of lines is like this. The number of points is like this, to be exact. The degree is 2n plus 1. And now we have x of complexity x, and takes maximal complexity, which is claimed to be n plus s, if s less than at most n, otherwise 2n. Recently, I learned that there is a programming language, Python, when they write a strange thing like this. This strange syntax they first write something, then condition, and then what happens if not the case. So it's like this.
Just one more question. Your claim is about this specific graph with lines and points.
Yeah.
You're not saying that it is true for every edge-transitive graph with sort of the endpoint on the left.
Definitely it's not true for edge. We will consider an example. So, for example, let's indeed consider such things. So imagine we have 2 to the n things, which are grouped into 2 to the n blocks of size 2 to the n, and we have a clicks here. So it's just a very the simplest way of when the common information is extractable, so to say. And let's see what we have here. So if we have some point here, its complexity it's a pair actually. Number of group and number of point. And now if we take the neighbors, we can change the number of point, change here, and here we keep things. So the question is how the complexity is distributed between these two parts. So if it's all concentrated here, then by choosing a good point, we can increase it. But if it's all concentrated here and the group is trivial, then changing the point will not increase it much. So this example shows that that's something very specific to our graph. Okay, so I think that there is enough blah blah. I said in Russian I would say conference. So someone is ready to prove the theorem. Please do it.
Yeah,
Sasha,
okay.
can you do it?
Yeah, I guess so.
Yeah, let's try.
Okay, so we have already shown that the maximal complexity is at most n plus s. Right?
Yeah, and of course it was 2n. So
Yeah, let's
this is
consider this
upper
case.
bound. Yeah, let's consider a case with smaller.
So, and now we have to show that it is actually attained somewhere. Well, more or less. By some.
Yeah.
Okay.
Also, I should say that everything is with precision of log n. So this is normal. Yeah.
So we assume that for contradiction, we have a line of complexity S where all the points have complexity much less than n plus s.
Significantly less than n plus s, I would say.
Yeah, I don't know, maybe minus some
E log n or something.
or delta.
Yeah.
Then we will show that actually what will be contradiction is that our line has lower complexity than s.
Yeah. So what we do is a contraposition. If all points on the line are simple, then the line should be simple itself. No.
Yeah. So, okay, how we show that this line is actually will be simple? Well, what we know is that all its points are simple. So, in the sense that their complexity is at most n plus s. So, all the points belong to the set of all points having complexity is at most simple points.
So you want to draw on the right-hand side, you want to draw a part which is contains of simple points somehow, yeah?
Yeah, so, and there are at most 2 to the n plus s minus delta simple points by just standard.
Yeah.
I mean, there are not at most that many simple strings.
And we assume that our line is such that all the neighbors are in the set of simple points.
Yeah. But let's now consider, let's consider on the left a set of all lines that have only simple points. Yeah.
Yeah, so actually we can enumerate this set because if line has all points simple, we can just see this while looking at the line at some point. So this is an enumerable set. Yeah.
Yeah, and so we will be done if this set has like at most 2 to the s elements
Elements, yeah.
or something. Well, I'm not really precise, but more or less, because if it has a small, it most 2 to the s elements, that using s bits we can encode our line by just the index inside.
Yeah, so if we allow logarithmic terms, we may assume that all the setting is given. We know n, we know everything. So we know the n and we know s, and so we can enumerate the set. And so only the ordinal number in this enumeration is needed to specify a point.
Yeah, and so the problem is, I mean, so we should disprove that this set can be big, can be much larger than 2 to the s.
And this is just a combinatorial thing. So if we have a small set on not a very large set on the right, then all the points whose neighbors are inside this set are there is not too many of them.
Yeah.
Okay.
So we kind of want to show that if I have a set of points that of size at least 2 to the s, then the set of neighbors of this set must be larger than 2 to the n plus s. Yeah. So we have to show that it is that it expands by factor of 2 to the n.
Yeah. The educated people call this expansion property.
Yeah, so why is that? And it's really simple. So we have, let's say, the first line, right, in this set. So let's just look lines in our left set just one by one, right? And we will use just a simple property that two lines can intersect just in one point.
Yeah.
And so, okay, so the first line contributes at least 2 to the n points, because I'm not sure about what is I mean, just imagine that it's not a projective plane. I don't know. Well,
in projective plane it will be 2n plus 1, but let's
yeah, I mean, constant factors here doesn't matter because it just gives.
No, n plus 1 will be 2 to the n plus 1 additional infinite point.
Yeah. So okay. So anyway, when I consider the second point, I know that its degree is also 2 to the n, but well, there may be some point. I mean, some point can be counted twice, but only one, because two lines have only at most one common point, right?
Yeah.
If my degree is d, then the first point, and it's like 2 to the n plus 1, right? So the first point gives me d point. The first line gives me d points.
Yeah.
D points. The second line gives me at least d minus 1 points, and so on up to like d, well, minus 2 to the s. Right? And we assume that we consider the case that d is like 2 to the n and s is smaller than n. Well, let's say for simplicity, right?
Yeah.
And then okay, so if you just sum it up, well, what it will be? Well, there are 2 to the s terms in this sum, right?
Yeah.
And if they are all small, I mean, if s is small compared with n, then they are all more or less equal.
No, small is a strong word. Imagine, let's assume that s is at most n minus 1.
Yeah, then all these terms are
at least
to the
s
d over
minus
2.
D over 2, yeah.
Then, so we obtain that indeed, our left set expands by factor at least d over 2, and d is like 2 to the n, and so we basically get what we need.
Yeah.
And when s becomes like n, well, this gives you 2n, right? This argument, yes.
Say it again.
I mean, so there are two. I mean, theorem has two statements. If s is smaller than n, then the maximal complexity is s plus n, and if it's bigger, then it's 2n.
Yeah.
Right.
Yeah.
I believe so. Like, so this just proves both statements, right?
Yeah, but we should be at least most careful. Be a bit more careful, because of course, if we have a combinatorial statement, if the if the set is of size 2 to the n, of course the left hand side is also of size 2 to the n. So it's not like this. So we should say that if imagine we should prove that for x whose complexity is close to n, we have a neighbor of complexity 2n. Imagine it has complexity 2n minus delta. Then we consider the set of size 2 to the 2n minus delta, and then we apply this argument to this set, which is valid because when delta is small but still something, and so we can conclude that there is something like n minus delta plus 1 or something like this. So this argument works.
I mean, yeah, so the point is that if I have already 2 to the n points on the left, any 2 to the n points, then they expand to more or less everything on the right. Well, up to a constant factor, maybe.
Yeah, but no, but the problem is that if you allow on the right something very close to 2 to the 2n, then on the left we have not 2 to the n, but 2 to the 2n, which is bad. So we should take a bit smaller.
What I'm talking about.
No, so there is we have a set on the right.
You mean you cannot show with this argument that we have a point of complexity 2n, but we can show that it has a point of complexity 2n, I don't know, minus 100.
Yeah. No, what I'm saying, that combinatorial argument breaks for this large thing. So you cannot say that if there is a set of size 2 to the 2n, then all the points which have neighbors here, they are at most 2 to the n of them, because they can be the entire left hand side can appear. So the combinatorial arguments needs the set on the right is at most 1/2 of the on 1/4 or I don't know 1/8 of the entire set. Because of this compromise here, but still it's enough for our purposes. That's all I'm saying.
Mm-hmm. No, you can actually, like, if you consider 100 to the n points, then they will expand to like 2 to the n, like 99% of everything on the right. But okay, but that's not doesn't matter here, maybe. Okay.
Yeah. Okay. So is it clear, this argument, what people will say?
Yes.
Laurent, if you hear us, is it clear now?
Yeah, it's pretty good. Yep, thank you.
Yeah, but maybe now you can explain the complexity argument, or anybody else can explain the complexity argument, just for diversity.
I am not familiar with the complexity argument for this.
Okay, but
Sorry. I
okay,
can
but
try to
then,
reinvent it, but that's-
okay, let somebody give the starting point. So
Great.
who can give the starting point? How the complexity argument should start? Let's switch to the next page. No. Let's switch to the next page. But this is some nonsense on this page. But let's clear it. So let's start with the complexity argument. So we take an x. and
So the
complexity
argument
of
will
x
be more
is-
complex.
It will be more complexity, but it will be simpler, but involve complexity more. And we need to find an point on the right, neighbor, y, that complexity of y is about s plus n. No, let's believe that s is just like a bit less than n, like 99 or something like this. So who can start the argument? What should we do first?
Assume the contrary.
No. And if we assume the contrary, we will get to the combinatorial argument. It's not, Sasha already tried this and he finished with the combinatorial argument. So how should we take, we need to find some y. Which y should we take?
Random.
Random. So what we can do is just to consider y who has complexity given x about n. So the degree is 2 to the n plus 1, but I don't write it. So there among them, there should be an x, a y which has complexity n. So what? So what is the complexity, for example, of the pair xy? Now. So
S plus L.
yeah, of course it's n plus s because it's s plus conditional complexity. And we want the this is we know, and we want that the complexity of y is n plus s. So we need to conclude that complexity of y is n plus s. So we need to all the complexity is in y. So we need that complexity of x given y is almost 0. So we need on every line there is a point that almost no, we want it to be for random point. So for most points that at least so we know that we can take a random point in probabilistic sense. So for most points we have all this, and so we need to find that on every one of these points at least almost determines x. On every line x, there is a point that almost determines x. Y. So we have a line x, and we know we want to find, and somehow knowing a point y, we need to reconstruct s. So what do we do? So what can we do to find x given some point y on it? So normally, of course, we have several points, several lines which go through y. So x is not uniquely determined by y, but somehow it should be almost uniquely determined.
Maybe line have complexity larger than S.
Yeah, so take a line which also has complexity less than X and goes through Y. So there are two properties. And we want this line to be X. And the claim is that for most points, it will create a good reconstruction. Why? Let somebody explain this. So for most points Y, X is the only simple line that goes through this point X. Why?
Yeah, let's consider all simple lines.
So imagine that's not the case. So then for most points, there are other simple lines. But of course, every simple line can go only through one point on X.
Yeah, so it affects only 2 to the S.
So if they are this line have complexity, all complexity smaller than S, there is smaller than 2 to the S lines. And so only 2 to the S points on the line can be bad. For all other points, X is the only simple line that goes through them. And so for them, we have complexity logarithmic here. And then we have complexity of Y n plus S minus O of log n. No, it's not a very. It would be nice to have it completely in the complexity domain. Not at the last time we also made some combinatorial estimate, but I didn't know how to do this.
What you are requesting is a kind of contradictory. You explained in the very beginning that we cannot we must use some combinatorial property of the graph. So in the proof there must be some point, some moment where you use something about the graph.
No,
Otherwise,
definitely. I don't. So the property of the graph is that it doesn't, in terms of the graph, it doesn't contain this things like this. Two lines intersect in only one point, or 2 points are only one line goes through 2 points, or things like this.
I don't understand to which direction you want to go. Do you want a proof which is as long as possible in complexity terms and which applies only to lines and points? Or you want to prove that would apply to similar graphs like points and two-dimensional planes and three-dimensional spaces?
Wait,
Yeah?
I mean, I think you can make at least one more step your complexity,
Yeah,
because
how do we do this?
because we want to so we want to say, okay, let's consider does our point get any other simple line? But we know that the point we have selected is hard given our line. But if the point lies on a different simple line, then obviously it is described by the second line given the current line.
Yeah. So what Misha says actually, if we want to formulate what we achieve by this argument, that actually we don't need to consider a random point in terms of counting and probability theory. Every point which has this property, which has Kolmogorov complexity, n is okay. Because points that do not determine X have bigger Kolmogorov complexity.
Smaller
Smaller
given the line.
Given the line, yeah. Yeah, actually, what is not so pleasant with this argument, that if we want to apply it to the case when complexity of x is n about, then we need then we cannot say anymore that from every point there is only one line, but then we need to estimate the number of lines which go through this point. This is a kind of disadvantage of this argument.
I mean, if we have a maximally complex line, then we don't even need to prove anything else, do we?
No, we need, if we have a not maximally complex line. No, we have a line of complexity n plus something. It's not maximal. Maximal complexity is 2n. So we have something intermediate like n plus d. And we want to show that there is a point which has complexity 2n. So we need indeed some additional argument. It's not like this immediately. How do we proceed then? So let's see it again. So imagine that we have a line complexity of x is n plus d. Then we know that complexity of pair is 2n plus d. And we want to find the complexity of y is 2n. How do we do this?
So we basically want to say that the complexity of x given y is at least d, right?
Is at most. We want to find y in such a way that this complexity is at most d.
Okay, so let y again be random given x.
So now at least combinatorially it's okay. Let's consider a typical point y. So if there are less than 2 to the d lines, then going less simple lines go through y. So if a few simple lines go through y, then complexity of x given y is smaller than d. And if more than a lot of lines go, then this point serves a lot of lines, and still two different points cannot serve common line. So we cannot have many points of this with this property. So it's again working. Yeah, and now I think maybe educated people like Andrei can explain something like this, that from this absence of rectangle, we can derive some spectral property of the graph, and from the spectral property of the graph, we can derive the theorem. Can we do like this or not?
We can.
How do we do this? Let's make a new page. No, or we turn to page number 3 because it's always nonsense. It's all full with some. So let's go.
What do you want to optimize? You don't have enough pages.
No. Actually, the next page is there is a picture of sphere. So I want to keep the picture of sphere, not to draw it again. But it doesn't matter. No, actually, I can draw a picture of sphere even now. But
okay, what is the number of the page?
Three. Page 3.
Okay, so let us try to explain why the spectral property is enough to prove this combinatorial and complexity statement. So first of all, what is the spectral property? So we have this bipartite graph with capital N. In your case, it's 2 to the 2n or something like that. And so
degree
we have
D, which is about 2 to the n.
Degree D, which is more or less 2 to the n. And let us denote M the matrix of this graph, which has capital N columns and capital N rows.
Yeah, just say it whether you divide by D or not.
No, I don't divide it by D. So each element of the matrix is either 1 if so in the row I and the column J, we have 1 if there is an edge between vertex I on the left and and vertex J on the right.
Yeah.
Or we have 0 if there is no such edge.
So the sum for each column and for each row is D, if I understand.
Okay, and also I think this is not terribly important. We could do something in a more general case, but let us assume for a while that M is symmetric. This is the case for your graph for lines and points. So the matrix.
No, if for projective things, yeah.
Well, for the projective plane, if we enumerate lines and points in the right order,
and x, y, z, and there is a symmetric ax plus by plus cz is equal to 0.
So if you've spent so much time to explain what is the projective plane, so let's
use it at least. Okay, good idea.
So we assume that M and M transposed is the same thing. Then we know from linear algebra that for this matrix, if we consider it as a linear operator, then it should have then there should exist a basis of eigenvectors with eigenvalues lambda 1, lambda n, and moreover we can compute these eigenvectors. At least I can compute the first one, which is equal to D.
First I should say that that's a bit stupid because eigenvectors are rather strange. So we have some vector on the left, and we get it transformed to get a vector on the right, and it is somehow corresponds to the left vector under this connection between left and right part. But still allowed to do it.
You're right. That's a more elegant or a more philosophically correct way is to consider a matrix of this graph, which would look like this, which would have a size, which would have 2 times n vertices, 2 times n rows, and 2 times n columns, and then we would study this matrix. But let us make things technically simpler. And just let us study only this part of this graph. Okay.
Let's stop here and let me ask. So there is it's written that there is a eigenvector which is has eigenvalue d. And what is this eigenvector? Lyosha, what is this eigenvector? Tell us. You have studied linear algebra in the university, and It was long ago, but there still is some eigenvector.
So if you cannot find this specific eigenvector, then you can try to find some other eigenvector for this linear operator.
No, it's more, I think, more complicated. Yeah. Okay, Kolya, do you studied linear algebra even longer ago? But you teach the course of linear programming, which should involve some linear algebra. So you should not be completely embarrassed by considering.
Moreover, I'm teaching the course about expanders now.
Okay, then you have no excuse, or maybe you're not a right person to ask.
Yeah, I propose to just before people say the answer to this question, I propose to pronounce some blah blah blah, which possibly will makes easier to understand. So assume we organize a random walk on this graph. So I start with some.
You mean a random walk?
Random walk.
Yeah, not random walk.
Walk.
Yeah.
Non, c'est pas un...
Yeah.
Le travail aléatoire, c'est balade aléatoire. Donc, we start from some point. And then take all possible, take a random neighbor of this point. Then we take a random neighbor of the neighbor. Then a random neighbor of the neighbor of the neighbor, etc. And we want to follow this process. We want to see what can happen. So we start with let us denote by a vector 1, 0, 0, 0, 0 the initial position, the point where we have started. Then, if I multiply this vector by the matrix M, I will get a vector with ones for neighbors of our initial point, and with zeros for other.
So that's why I suggested to divide it by d, so it will be just the probability distribution. On the
okay, if you divide it by d, then we will get 1 over d, 1 over d, 1 over d for all neighbors of our initial point, which corresponds to the probability to find ourselves on this or that point. If we do one more step of the walk, then we will get a new distribution of probabilities, which is m over d, or m divided by d square applied to the initial vector, etc., 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 etc. So if we do, I don't know, k steps of a random walk, then we should multiply the initial vector, the vector of the initial distribution, by m normalized m to the k applied to the vector. So now we have a kind of, I don't know, physical meaning of eigenvector. The eigenvector should correspond to, okay, I'm cheating a little bit. An eigenvector corresponds to a distribution of probabilities over points, which shouldn't change much when we apply one more step of the walk. It should be only multiplied by the... No, in my picture it was one step, because we had distributions on the left part on the step with the even number, and a distribution on the right for the steps with odd ordinal number.
So now let's ask our expert in probability theory. Imagine we do just 2 steps of this walk for this specific graph of lines and points. What kind of distribution we get on the left side? Misha, tell us what the distribution is. So we take a point, given point, then we draw a random line and take another random point on this line.
I think the initial point has a little larger probability than all the other points, but all the others have the same probability.
Yeah, of course, there are more chances to go to initial point because it always is there. But all other points are have the same probability. So first we need to draw a line that goes through it, and then we should select the same point, the correct point. So both steps give the same probability for all the possible points. So,
but what you're saying is correct, but it's kind of diversion. You asked first what is an eigenvector number one. Now we are discussing a different question, which is, in my opinion, more delicate and less trivial. What is the square of our matrix? Now, it's an interesting question, and indeed, at some point we should study it. But I think we can answer the question about the first eigenvector even without understanding what is this m square.
And even without asking what?
The uniform probability distribution.
Yeah. You don't need, as my friend Levitov says, не надо быть зоотехником, чтобы, значит, сказать, что это равномерное распределение. So one doesn't need to be an expert to find that's uniform distribution. And now experts in linear algebra should remember that if we have one eigenvector, then we have our operator is acting on the space of all the one-dimensional space of this eigenvector, and also on orthogonal space. And what is this orthogonal space here?
The space of all vectors where sum of coordinates is 0.
Yeah, so we have a kind of a average zero vectors, and if we make apply this matrix to average zero vectors, it gives all the rest of this operator.
So we know in advance that all other eigenvectors can be chosen in such a way that the sum of their coordinates is 0. You're right.
Not only can, but they should be chosen in this way.
No, actually, we still don't know it. Well, who knows? Maybe there are some other eigenbases with a different properties. Yeah, you're right. If we start with this E1, then the other should be in this subspace.
No, but also we know that any orthogonal basis will contain E1 and some orthogonal basis in the subspace.
Honest, I don't understand what we are doing now completely.
So
what we are talking about?
No, we are finding the eigenvectors of this matrix.
I remember that the second eigenvalue is very small. It's like square root of d, I guess.
Yeah. Do you remember? But Sasha, say something.
I mean, so what we want to do is that we want to show that this graph expands using spectral dimension.
We just try to understand what are the spectral eigenvalue of this matrix.
Yeah,
we understand that they correspond to random walks.
Do we consider that expanders or something?
No, we consider a specific graph of points and lines now for a while.
And well, just usual affine expanders with square of q square to event, something like this. The second. Okay.
But so we don't do anything serious. We just try to be accustomed to what is random walk, why it corresponds to a matrix, and if we go back and forth, it's the square of the matrix, and what are the eigenvalues, and we say that there is an invariant space with eigenvalue 1, and the orthogonal invariant space, and now Andrei will tell us something about all the other eigenvalues, that they are, namely, that they are all of square roots of D.
Yeah, now I make so what we were discussing before was more or less trivial, and we more or less proved it. Now I'm making a statement which is not terribly difficult, but at least now we have no proof of it. I'm claiming that all other eigenvalues except for the first one are much smaller than the first one. They are all they are at most this big O of square root of D. Now, frankly speaking, I do not remember the precise answer. Maybe it's even something like precise square root of D, or something like precise 2 times square root of D. But certainly of this magnitude.
Yeah.
And
so
now
we compute this.
To compute this, actually, we instead of computing the eigenvectors of the matrix M, we should compute the vectors of the matrix M square, because M square has a really simple structure.
So it has D on the diagonal, I guess, or more or less.
More or less, not exactly D, probably D minus, maybe D minus 1 or something like that. More or less D minus 1 on the diagonal, and
but why
1.
D minus 1?
No, exactly just D, because we go in D ways there, in one way back.
Yeah, there are D paths.
There are D paths of length 2.
Yes, you're right. You're right. Exactly D on the diagonal.
We have just exactly one path. Yeah.
Yep. You're right.
But D minus 1, I know why you want to write D minus 1, because it's just a matrix which is made of all ones plus diagonal matrix D minus 1, D minus 1.
Mm-hmm. So we know it's spectrum.
So the spectrum of this matrix is just D 0, 0, 0, yeah?
Yep.
And this is the unit matrix times D minus 1. So the entire thing.
Wait. Is it D? Is it D?
No, it's not D, it's N. Sorry.
N.
N 0, 0, 0, 0. Because the eigenvector, which is constant, is multiplied by N.
Yeah, which is in our case D square, but yes, okay.
Okay, so it's N 0, 0.
What is capital N? It's D squared.
This is just this. So we know that the M square has this spectrum. So it has spectrum N plus D minus 1, D minus 1, D minus 1.
Yeah, it was the spectrum of M square.
Yeah.
And the eigenvalues of the original M must be square root with some pluses or minuses, but square root of this.
Yeah. Yeah, so we have contradiction because we know that the first eigenvector is D. So we should have the D square should be equal to N plus D minus 1. But if we do everything correct, it will happen. If we count the lines and points accurately, it will happen.
Yeah, because N is not exactly
D square.
It's not exactly D square or something.
Yeah. So it's 2 to the N plus 1 square is 2 to the 2N plus 2N plus 1 plus 2 to the N +1, -1. So yeah, you know exactly. You won't believe me, but it's exactly true.
So if we do this arithmetic exercise carefully, or if we believe Sasha, then we see that the first eigenvalue is indeed D. We should get it one more time, the same bound, not about the same value, and all other eigenvalues are plus or minus, plus or minus of square root of D, or D minus 1. Yeah, probably D minus 1.
So it's kind of
I'm
great
sorry.
equalize.
I'm
Yeah.
sorry, but you have a picture in the left bottom corner, which shows that it's not so simple.
No, it was
for-
a picture. How can
For
the alternative
bipartite
deal
graphs,
with things?
you have an eigenvalue -1 also, minus this.
Yeah. This is why I avoided studying this matrix, which is the real matrix of the graph, and I avoided computing the eigen values of this matrix.
We didn't consider this. We agreed that we identify the left-hand side with the right-hand side using our projective plane symmetry, and in this way we need only one matrix.
So you just explaining the same result about projective plane.
Yeah. We're explaining the same result.
I thought that the idea was to put some spectral conditions for a graph such that theorem is true under these conditions.
It was.
In this case.
Oh, no, it was. Well, actually, I can add here a short comment for experts. If we want to study this the real matrix of this bipartite graph, which is written on the left, then essentially this argument that we have just performed, it will give us that this matrix has eigenvalues plus D and minus D that are, so to say, big, and all other eigenvectors will be plus or minus square root of the same degree D, but there will be twice more of them.
But let me make a competing remark for expert. I think that the better for a matrix, actually, we have for a matrix which makes one Euclidean space into another space. Actually, there is another notion of eigen, not eigenvectors. There is a basis, orthogonal basis this and this, which make the matrix diagonal, and we should consider these numbers. But okay, forget about this. Anyway, for our special case of projective plane, we have the result here is O of square root of D. Why it gives something we want, something for complexity?
I think it's a better idea to erase everything here. It would be a better idea to go to the next page.
Sorry,
Okay.
so what you want? You want to show that whenever we have this kind of gap, D square root of D, then we also have a complexity result.
Yes.
Yeah.
Because of expansion. Okay.
Yeah, let's go to the next page, which is page 4. So let's go to page 4.
I see lots of things on the page 4. Is it okay?
No, it was our previous page, but we can now erase all things.
Or we can go to the page 5.
But it contains a sphere, you know. Okay, let's duplicate page 4. So it does.
By the way, it's not clear how to come up with other examples of such graphs with such gap.
No, actually, the idea is that we can consider, for example, lines, points, and lines in three-dimensional space.
Or points and planes in three-dimensional space.
Or something like.
Will they have?
No, more or less, if we put a random plane through a point and then take a random point on the plane, we also have all other points more or less with the same probability.
No, actually, if you take points, if you take points and planes, then you'll have essentially the same nice property. If you take points and lines in the three-dimensional space, then I think the bound will be slightly weaker. It will be not square root of the degree, but it will be something other.
But at least it's more or less in all the symmetric things. The two-step process has some advantages.
I believe that for points and lines, 2 steps is not enough. You need to consider longer walks, and this will give a weaker bound.
Yeah. Okay, so now I can erase this. Keep the graph, but erase all the others.
We can use page 11 or 10.
Okay, but we already have a nice graph here. Why it doesn't want to why I erased something? Why it doesn't? Oops.
And do we really need square of D expanders? That's
I guess we need square root of D to get exactly this bound with n plus s, with all s's.
Yeah. Okay, let's
even if D is constant.
Okay, what is K?
D.
D.
In the previous construction, D may be constant. Ramanujan graph, say.
Okay.
No, I'm not sure about that.
Let's finish the argument for projective plane. So finally I managed to erase things, not erasing another things. So on page 4, you can write whatever you want.
On page 4?
Yeah. On page 4, you write whatever you want.
Yes, I'm comparing pages 4 and 5. Okay. Page 4.
Yeah. Yeah. Because I erased the wrong page, but don't worry. Just write something.
Okay. I will try to sync you changes. Can you see what I'm drawing? No, you cannot, because I cannot draw anymore. Okay, I will try to reload the page.
You draw something on page 4, or somebody else is drawing something.
No, that was not me.
Okay, just go out and go again, like in car.
Okay.
Yeah. Okay.
So I will try to formulate a combinatorial statement which is enough to prove your complexity statement.
Yeah.
So we take two sets A and B in the left-hand side, in the left part and the right part of the graph, and we assume that all neighbors of all vertices of A belong to B. They're inside of B.
Neighbors of A belong to B. Yeah.
And we assume that the size of B is approximately 2 to the
n plus s.
N plus s.
And you want to conclude that the size of A is at most 2 to the s.
Yeah. So let us look at the edges between A and B. On the one hand side, the number of edges between A and B. On the one hand side, we know exactly how many edges do we have. It is A times degree, because all neighbors of A.
And so it's no additional requirement. Yeah.
On the other hand, we have a statement which is usually called this expander mixing lemma. Expander mixing lemma, which claims that this number is not bigger than what? It is not bigger than n times the size of A, the size of B, divided by it was a capital N. Okay, let me draw the capital N, which is
so it's just expectation for random edges, so to say.
Yeah.
If everything was random, then we have only d edges out of n. So instead of A times B edges for the full graph, we have smaller part of this. Yeah.
Yeah. Just I can just draw what you mean. We take A vertices in A. We have D neighbors of each of them, and so to say, typically the probability to get into B is B over N. So all this product corresponds to the average number of vertices in a random situation. But we're not in a
term.
I should say that this inequality means that size of B is at least n.
B is at least, yeah. Good remark. But this is not all. This is not all. We're not in a random situation where some specific A and B. So typically we should add something, and this something is the second eigenvalue, or formally the absolute value of the second eigenvalue, square root size of A, size of B. So I'm not saying that it should be obvious somehow immediately that this inequality is true, but everyone who has followed or who has taught a course of expanders certainly know that this is the case, and the proof is not terribly difficult.
No, the idea is just you consider some so you consider a function which is kind of a function which is on A concentrated, and the function is concentrated on B, and you compute M FA FB. Somehow it's and has average 0 and average 0, so the first eigenvalue disappears, and you have only the second eigenvalue, and then you get the bound. That's what we should do, or something else.
Yes, but I'm afraid those who know the proof, they know it, and those who don't will not understand you.
No, it just I want to say that just you apply some you just use some special functions, nothing deep here. It's just
nothing deep.
So let me now try. Say we have A times D is greater than A times D times B divided by N plus what is
so it's square root. Or some big O square root of D. It's not very important.
Yeah. Okay. Then A is A, and B is what should we write? N or A times D?
Okay. Right B.
Yeah, we should write B here. Yeah.
And possibly it should be big O of this, just because I'm not sure that the second eigenvalue is just square root of D and not 2 times square root of D. But actually, since what we want to know this complexity statement, it's on the logarithmic scale, we will be interested in logarithm of A, logarithm of B. Then actually, when we take a logarithm of the left-hand side and of the right-hand side, then on the right-hand side, what is important is only one of these two terms. So one of these two terms in the sum must be bigger. And when we take logarithms of these things, so it will be essentially a logarithm of maximum of these two. So guys,
there was even a special lecture which academic Maslov told to Vereshchagin, I guess, about this. You told me about this one. That if you take logarithm, then the sum becomes the maximum.
It's called tropical mathematics.
Yeah.
Okay, so I proposed just to write two versions. I want to write the logarithmic version of this inequality, and I propose to write two different logarithmic versions of this inequality.
If we look
for the case, when
that B is at least n.
Yeah. Can we erase something here? Maybe
sure,
this stuff.
Sure, we can erase this.
So there will be two logarithmic a very radical solution. Okay. Okay, so the first logarithmic version of this inequality is that A times D is not bigger than A times D times B divided by capital N. It looks pretty stupid, but we need it. Yep. And the second version is that A times D is not bigger than O of square root of D times A times B. So 1 and 2. So when we take the logarithm, we will get either the first, either second. We don't know in advance which one.
So this is B is equal to omega of n.
Yeah, but it's I think it's even the redundant information. You can erase it. It's too many details. Forget it. Okay, so let us try to write the logarithmic version of the first inequality and of the second one. I think it must be especially simple for the first one. So in the first case, we can simplify these, we can simplify that, and what we get is that logarithm of the size of B is bigger than log n minus a constant, which is in our case 2n minus a constant. And
in the special case we have for large B, we have a special.
Yeah, and this corresponds to the case where when complexity of a point of this maximum complexity of a point in a line is about 2n. Okay, now let us possibly not the logarithmic, just still on the linear scale. Okay, let us understand what do we have in the second inequality. If I take the square, so if I take the square on the left and on the right, we have this thing, right? So we can simplify A and A square, D and D square, and we get what remains is B is bigger than A times D. So on the logarithmic scale, we have log B is bigger than log A plus log D
Which
minus
is n plus s. Wanted to.
Yep, this which is s plus n. So it was a combinatorial statement, and we translated it in the usual way in a complexity statement. Then log log A corresponds to this complexity of the line, which is s, and log B will correspond to the complexity of the point in the line, which is complexity of y.
Yeah, but in this way we use more about projective plane. Not only that there are no quadrangles, but also kind of uniformity which we don't use before. Somehow this argument is more general, but also more it requires more from the graph.
Yes.
Okay, so what now I want to say some general things and finally show the sphere. So so what I would like to have is kind of general answer for arbitrary graph or for some specific graph. What kind of what is a spectrum somehow? We have a line of given complexity, and what can we know about and take complexity of all points? So what is possible here? Or so we have a string of n bits and look at Hamming, all this Hamming ball, and look at all the complexities, what we can say. And also there is very specific thing, which is a real version of these things. So imagine we have a projective plane, so that's where the sphere is needed. We have a projective plane, and we consider kinds of points of this plane with 2 to the minus n precision. On the sphere, on the 2 to, so the point is now a line going through.
Can you tell us on which page you are now?
Oh yeah, I'm stupid. Sorry. I should. Yeah. Where the sphere is. So what I suggest is now consider more or less consider points on the sphere, or a projective plane is actually the sphere because we should just identify the points on the other opposite points. But let's consider just the sphere. And consider them with 2 to the minus n precision. So we have about 2 to the n different points. And again, we can consider that A and B are orthogonal with the same precision. And for every point, we have approximately 2 to the n orthogonal points. And then we can ask, so imagine we have a kind of a real point of given complexity S. And what can be said about the maximal complexity of these points, or minimal complexity of these points, or average complexity of these points? What can we say if we know the complexity of S? And I just wanted to tell you that I don't know any serious answers, but there is one specific answer due to Ilya Bogdanov, and the answer is like this: if complexity of X is about S, then there is a point Y orthogonal to X, whose complexity is n plus S over 2. Theorem. And this is somehow related with the combinatorial or now geometric statement. Imagine we have a set A and a set B of the same with the same property, all points. Now we consider exact points. So we have a set of points on a real sphere and some kind of a set B also on it. All points orthogonal to A are in B. So how? What is the minimal possible size of A? And Ilya Bogdanov, I don't know whether he was the first or maybe he knew it from somewhere, but he invented or found extremely funny and strange arguments, which I cannot imagine how one can get. Maybe Misha understands this better. It says that A is at most area of A is at most square root. No. In other direction. Area of B is at least square root of area of A. So if area of A is it's normal if A is small near the pole, then B is kind of a zone under near the equator. So S of B can be larger than square root of A. It's the area of A, but still it cannot be. There is kind of serious inequality, and an exercise which I think you can solve without Bogdanov is that S of B is greater than S of A. It's almost not completely trivial, but that's I understand how one can invent this, and this will imply this thing. And now the question really is...
It's very strange. I'm confused.
Yeah.
So
why
S of A is less than or not?
No. I assume that sphere is it's unit sphere. So everything is now measured in real area.
So the radius is 1.
Okay, let's even assume that the area of the sphere is 1.
Okay.
Is 1. Then I think we don't need any coefficients here this evening.
So what is given, A or B?
No, it doesn't matter. We can start with A and then consider all the equators which are orthogonal to points in A. Or we consider starting in B and consider all the points which have equators entirely in B.
I'm sorry, maybe I'm missing something. So as for the second inequality, simple one, so we can just rotate it by some 90 degrees. So the
around
of
what?
A will be
around some point.
I'm not sure.
No, of course you can rotate it, and then all this will be, all these points should be in B, definitely. But the bad thing is that this rotated set can intersect with the original one.
It should be that. I mean the exercise, because considers A the entire, then B is empty.
No, if A is entire sphere, then B is entire sphere, because we, for every point in A, we take all these neighbors, all orthogonal points. And so we'll have entire sphere.
So it's a union. It's a union of all orthogonal points.
Yeah, it's exactly what we see, that if A belongs X, if X belongs to A and Y is orthogonal to X, then Y should belong to B. This is exactly the same property we consider all the time. But now we consider it in geometric setting.
What's the problem with this argument that we rotate A by 90 degrees?
if we rotate,
I mean, just rotate. I guess just if we rotate it, well, take any axis which.
Yeah. Sorry. No, the exercise is more trivial than I think. Yeah. It's stupid. Yeah. No, I thought a more complicated argument, but indeed you can rotate things. Yeah. So, sorry.
Maybe you can... Wait, excuse me. Maybe here we should ask people, can they still follow your talk, or it's a moment to stop and postpone it till
anyway, we have
Monday?
to stop it now. Anyway, we have to stop it. But what I want so people will, next time, people I think will explain, maybe give some answer to this general question. So consider one of these graphs, a Hamming graph, or projective plane graph, or this real projective plane graph. And then the question is, what we can say about the spectrum of the distribution of the complexity of neighbors if we know a complexity of a point on the left point. So if we know the complexity of a line, what can we say about the complexity of the points? So this is one answer which I can provide for this following Bogdanov argument. But maybe someone will come next time with a full answer for any graph and for maximal, minimal, and average complexity, or whatever is. So, for example, imagine we have a line on projective plane. So we have different complexities. There is something minimal complexity and maximal complexity. Does it mean that we have more or less all the complexities in between, or not? No, with some reasonable precision, of course. So we have a line on the projective plane and have 2 points. And the points can have different complexity. The question is whether we can be sure that there is all complexities between these points are also appearing on the line. And this is somehow connected to this line and point problem for Hausdorff dimensions, but this is a different story. And I think we... Okay, so I think this is a good place to stop. If there are some questions, let's ask them.
I think about the exercise, it probably should have been with factor 2. Like S of B should be larger than 2 times S of A.
Not exactly, because if A is an entire sphere, it cannot happen like this.
Well, but probably with some, I don't know, limitations.
Yeah. I understand where did you get. So you can rotate A in different ways, somehow like this and like this, and like this, and have a triangle like this. But still you cannot derive these two things. Constant 2. But there is much better inequality for small a's, which says that. So for if A is large, you cannot have factor 2, and if A is small, you have much better factors here. Okay, so any other questions or comments or whatever?
Do you think that the spectrum of a graph is derived what you want? So it depends on the spectrum of graph.
No, definitely spectrum. I don't know. Spectrum of a graph plays an important role, but whether it will be enough to get an answer, I don't know. that's and what is the spectrum here for this real orthogonality graph? I also don't know. And indeed, if we take on a sphere, if we go back and forth, we don't have the uniform distribution. We have a distribution which is concentrated near x, of course, because you have much more probability to come close to x if you go there intersect somehow in different ways. So not clear. Okay, then probably we can, if we don't have better suggestions, we can continue this discussion next time or make a break, and if we have another talk for next week. But Andrei, do we have another talk for next week or quiet?
I'm not aware of any plans.
Okay, then somebody will solve this problem, I hope, and will explain the solution next time.
Okay, so then let us pause the
problem.
recording.
Yeah, okay. Good.
So if somebody wants to ask questions without being recorded, then you're welcome.
Okay. Yeah,
No, somebody